Alright, so now let's go down through the solutions for the digital logic practice problems. So the first problem here was just what's the truth table for this 4-input AND gate. So it's a 4-input AND gate here, which means we're going to have 2 to the 4th. There's 16 possible inputs here. And it's an AND gate, so we know the output's only going to be 1 when all the inputs are true. So here's our truth table here. We're going to have one column for in 1, in 2, in 3, and 4. Sorry, 0, 1, 2, 3, and 4, and then our output. And so here's the result. As I said, you got 16 rows. It says all possible combinations of these inputs, and the only value that's 1 is the last one down here. Here's another truth table. What's the truth table for this circuit? So this circuit has 2 gates here. We've got A and B going into an AND gate, and they generate E coming out. And then E and C go into an OR gate, and they generate D going out. So we've got 3 inputs here, C, B, and A, so we're going to have 2 to the 3rd, or 8 possible combinations of inputs. I have 8 inputs here. And we want to see how this circuit works. So here's the answer for this. I put all possible combinations of C, A, and B together, and I've calculated what this E input here will be. That's just A and B, and what the output of D is. So let's take a look at these 2 cases here. These are the cases where E is true. So E over here is only going to be true when A and B are both 1. So there are 2 cases where A and B are 1. That's when A and B are 1 and C is 0, and when A and B are 1 and C is 1. In both of these cases, A and B are 1, so E, which is A and B, is going to be 1 as well. And what we see here is that when E is 1, we have a 1 going into our OR gate, so it doesn't matter what C is. As long as one of the inputs to the OR gate is true, the output's going to be true. So in both of these cases, the output is true. Now what's the other case where the output of this circuit's going to be true? Well, those were the cases where this input to the OR gate is true. The other cases are where the C input to the OR gate is true. And here are those cases here. Whenever C is true, we also have the output being true. So here's the truth table for this circuit. Let's go the other way around. Let's take a look at this logic function and try and figure out what it is from the truth table. So here's a truth table, and we look at when this function here is true. And it's true in these 3 cases. So it's true when B is true, or when A is true, or when A and B are true. So if I look at this together, this is just an OR. So this is true when either A or B are true. So the logic here is just A or B. And remember, you've seen the OR circuit before, seen it a bunch in the lecture as well. And here it is. A or B are true, and here both of them are true, so it's true as well. Now let's take a look at a logic blocks here and figure out what this circuit does. So I've got a bunch of inputs here, and we want to figure out what the output is. And the inputs have their most significant bit here and their least significant bit here, and you can see how those correspond to the inputs to the circuit here. So let's walk through this circuit and figure out what it's doing. So the first part we have here is an encoder. And the encoder is going to take a 1-hot input and convert it to binary. So one of these values can be true, and I'm going to get a binary value out here which tells me which one it is. Then I've got a decoder here, and the decoder is taking the output of the encoder. So this is going to take the binary value and convert it back to a 1-hot value. So I'm going from 1-hot to binary to 1-hot. So what I expect to get out here is this same value as I had on the input. I'm encoding it to binary, and then I'm decoding it from binary at the end. Let's look what happens at the top up here. So here, this demux here is going to take its input and send it to one of the 4 wires here. Which wire? Well, it's what comes out of the encoder. Then what's the mux going to do? The mux is going to take one of these 4 wires as an input and send it to the output. Well, which wire? Well, again, the input for the select here comes from the encoder. So this is going to send out the value to one of these wires, and this is going to take in the value from the same wire. So what do we expect to have happen here? Well, we expect the value to go through here. It's going to go to one of these wires and come out the other end. So we expect the same as the input here. So in reality, it looks like this circuit doesn't do anything. It's just a really complicated way of taking one input and printing it back to the output. So let's walk through these values here and see how they work. So here's the first value. And before we go through that, let's define which ones are input 0 and 3. So here's the most significant bit, that's input 3 to our encoder, and here's our demux here, it has outputs 3 through 0. So here are the most significant parts of our input. We've got 1, 0, 0 on these inputs to the encoder, and we've got a 1 going into the demux. So what happens here? Well, the encoder has a 1-hot value, and that value is 3. So the encoder is going to take that 1-hot value 3 and convert it into a binary 3, or 1, 1. So now I've got 1, 1 on this output here. What's the demux going to do? Well, it takes its select this 1, 1 or binary 3, so it's going to take its input and send it to output 3. So it's going to send the input through to the output here, and we're going to get a 1 going through on this wire. Now we've got this 1, 1 or this 3 coming through here to these other wires, and so the mux is now going to get a select, which tells it to select input 3 and output that. So it's going to take this same value and output it. So we're going to get a 1 coming out here. What's the decoder going to do? Well, the decoder here is taking its input of 1, 1 or 3, and it's going to convert it into a 1 hot output. So we're going to get 1, 0, 0. So if you look at what we got here, it's the same output. So 1, 0, 0, 0, 1, our input was 1, 0, 0, 1. So for this one, we get the same output. Now if we look at the next value here, we're also going to get the same output. All we've done is change the least significant bit to 1 to 0, so this will be a 0, but it'll still follow the same path through the circuit. Let's take a look at this value next. So for this value here, we've got 0, 0, 0, 1 on the input to the encoder and 1 going into our demux. So the encoder is going to take a 1 hot 0, that's input 0 is true, and it's going to output a binary 0. So this binary 0 is going to go into the demux up here, and it's going to take its input and send it to output 0. We're going to have that input coming through onto output 0. We also have the same 0, 0 from the encoder is going to go into the select for the mux. So the mux is now going to have select input 0, which is up here, and it's going to send it to its output, so we're going to get a 1 on the output. So the same output here is the input. Not surprising, that's what the circuit does. Down at the bottom here, we're going to take in the 0, 0 binary into the decoder, and we're going to decode it to a 1 hot output, and the 1 hot 0 output is going to be 0, 0, 1. We have output 0 here, have a 1. So we got the same output as before. And you can go through this and find it's the same value for the same effect for the next one. Now let's take a look at this last value. So for this last value, we've got 1, 1, 1, 0 going into our encoder and a 0 going into our demux. Now what's the encoder going to output here? Well, this is sort of a trick question. This isn't a valid 1 hot value. It's not one of these things that's hot, 3 of them are hot. So we have no idea what the output is going to be here. This is an invalid input to an encoder. So we don't know what's coming out of here, which means we don't know what the demux is selecting, so we don't know what its output is going to be. We don't know what's going into the select for the mux, so we don't know what the output is here. And for our decoder over here, we don't know what the input is, so we don't know what the output is. So we don't know either of the outputs because this circuit requires that these 4 bits be a 1 hot value. So what do we get when we put this into the circuit? No idea. It's undefined. So overall, what does this block of logic do? Well, the output is just the input if these 4 most significant bits are 1 hot. If they're not, then we don't know what the circuit does. All right, so let's take a look at state here. So here's the picture we had for state before. We've got some logic, which takes in our current state, takes in our inputs, and generates our next state. And then we've got some sort of memory, which when the clock comes on, takes the next state and makes it become the current state. So we looked at a counter, and let's explain what all of the different parts of this are in the counter. So what are our inputs for the counter? Well, a counter is going to count up by 1, so our input's just going to be 1. So we've got a 1 going into our next state logic. What are the outputs? Well, it's the current count. We're building a counter. It should tell you what the count is. So the output over here is just going to be the current count. What's the next state value here? Well, the next state value is going to be the current state, or the current count, plus 1. It's the next count that we go to. So this right here is going to be current count plus 1. And what's the current state? Well, the current state is the same as the output here. It's going to be the current count. So we take our current count, and that's our current state. Now, what logic do we use to take our current count, our input of 1, and give us current count plus 1? Well, we just need this plus part, so this is going to be an adder. So our next state logic is an adder. And then finally, what's our state memory here? Well, it's going to be a flip-flop. So when the clock edge comes through, it's going to take the input, the next state, and move it to the output. Now let's take a look at latches. So we went over latches a bit in class, and you'll notice this latch is a little bit different. So first of all, it has not clock going into both of these switches here, and we've got an inverter here. And the inverter here is just because if we write in a 1, we'd have a 0 going out, and we invert it, so now when we write in a 1, we have a 1 going out. So let's see what happens with this latch when you actually use it. So in the first case here, we have clock equals 0, and we've got an input of 0. So with clock being 0, not clock is going to be 1, and not clock is going to be 1. That means both of these switches are closed, so when you write in a 0, the 0 is going to go into the first latch, and then straight through the second latch and out the other end. Now what happens when we change the input to a 1? Well, clock is still 0 here, so these switches are still closed, and the value is going to go right into the first latch and right through to the other one. So this looks a lot like our original transparent latch where the value goes right through. Now what happens when clock equals 1? So when clock equals 1, we still got our input of 1, but it can't go through anymore. Because when clock is 1, not clock is 0, so this gate is open. Same one here, this is open. So it doesn't go through. We still got a 1 in here. Can't move that to the last latch because that switch is open. So we still output a 1. Now what happens if we change the input? Well, it's still, we can't go through, so it's going to stay a 1, and we're going to keep having a 1 here. So what is this design equivalent to? So this is a design where clock equals 0, the data goes right through, and when clock equals 1, it stays at whatever the last value is. So this looks like our transparent latch with an inverted clock. Remember, the transparent latch, the value went through whenever clock was 1 or high. Here it goes through whenever clock is 0. But this is slower because here you have to go through 2 latches to get the data out instead of just 1. So this really isn't a very good design for anything.